People enter. It's my bound duty to introduce three resource persons who are waiting to shower their knowledge and keep the audience alert and make them to learn more. Day 1, resource person Dr. E. NATARAJAN, Associate Professor of Mathematics, Indian Institute of Space Science and Technology, Department of Space, Government of India, Trivandrum, Kerala, with the topic Mathematical Analysis of Finite Elements Methods. In day 2, Dr. A.K. Abdul Hakim, Assistant Professor of Maths, SRME College of Arts and Science, Coimbatore, with the topic Applications of Mathematics in Real Life. In day 3, Dr. M. Kyle Willy, Assistant Professor of Mathematics, Government Polytechnic, Warg and Dauman, with the topic Heat Transfer, a Mathematical Approach. Today, we are going to have Dr. E. NATARAJAN Sir, Associate Professor of Mathematics in the Institute of Space Science and Technology, Government of India, at Trivandrum, Kerala. He completed his Doctor of Philosophy in IIT Madras in the year of 2008. Also, he did postdoctoral fellowship in a University of Henri Poincaré, France in 2008-2009. His field of research is virtual element methods for nonlinear problems and multigrid techniques. There is a PhD scholar under his guidance. Also, he completed ISRO projects. He visited many foreign countries like France, London for academic purpose. Also, he published 15 research papers. He's now today he's going to talk about mathematical analysis of finite element method. Sir, I humbly hand over the session to Dr. E. NATARAJAN. I request all the audience to mute their volume. If any questions, please raise your hands and chat box is open for the queries. Thank you. Principal ma'am.
Hello. Hello.
Hello sir. Sir, சொல்லுங்க sir. சார் நீங்க ஸ்டார்ட்
அந்த
பண்ணுங்க சார்.
ஸ்கிரீன் ஷேர் பண்ணணும் மேடம். நீங்க அந்த இது ஷேர் பண்ண முடியல ஸ்கிரீனை.
ஒரே நிமிஷம் சார், ஒரே நிமிஷம். சார் இப்போ ஷேர் பண்ணுங்க சார்.
ஓகே. ஓகே, தெரியுதா ஸ்கிரீன் தெரியுதுங்களா?
தெரியுதுங்க சார், தெரியுதுங்க சார்.
ஓகே, ஸ்டார்ட் பண்ணலாமா?
பண்ணுங்க சார்.
ஆடிபிளா இருக்கா? இஸ் இட் கிளியர்? ஆடிபிள்?
ஆடியபிள் சார், ஆடியபிள் சார்.
Okay, fine. Okay, so good morning to everyone. Okay, so today I thank the organizers for giving me this opportunity to give a talk on this subject. Okay. 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 So today I am going to talk on finite element method. What was the how this technique has been developed and what is the background of this technique? Okay. How it is applicable and so on. So that is those are the topics, things we are going to discuss in today's lecture. So usually this talk I am going to fix only to an ordinary differential equation. So consider this ordinary differential equation minus u double dash equals to f of x, which is an elliptic equation with the boundary condition u of 0 is 0, u of 1 is 0, zero boundary condition. And of course you can extend this to two dimension, minus uxx plus uyy equal to f of xy. Xy belongs to omega, and on the boundary the function u vanishes, u is 0 on the boundary. We are expecting that omega to be a bounded open bounded domain in the xy plane with the boundary dou omega. This technique, so when you see what is the purpose of numerical technique, so whenever a differential equation, when a physical phenomena is modeled into a differential equation, we are looking for the solution. We are trying to solve the equation. and for most practical purposes, we don't know the exact solution, or we don't have we don't have the method. We don't have the method to solve this. Hello, hello.
சொல்லுங்க சார்.
மேடம் ஸ்க்ரீன் வேற யாராவது இது பண்றாங்களா? ஸ்க்ரீன்ல லைன்ஸ் எல்லாம் வருது. ஐ டோன்ட் நோ ஹவ் இட் இஸ் கமிங்.
அப்படிங்களா சார்?
ஆஹா,
தெரியலீங்களேங்க சார். பாக்குறேங்க.
யார் ஆப்ரேட் பண்றாங்க? ஓகே, ஃபைன். யா, ஓகே. ஸோ finite element method. So any numerical method. So there is no exact solution, and given a differential equation, we do not have an exact solution. So we should resort to differential equation. So we resort to numerical solutions. Okay, we resort to numerical solutions. So there are several numerical solution techniques are available: finite difference method, finite element method, finite volume method, mesh free method. Several techniques are available. Especially finite element method has attracted a lot of engineers over several decades. People are very much interested in obtaining solutions, numerical solutions, using finite element technique. Okay. Now, okay, to explain how the finite element method works, okay, let me start with a basic
அப்படிதானா? நான் தான் நேரமே ஆன் பண்ணி வச்சுட்டேன். ஒரு நாள் இப்படிதான் இடையில போன் பேசிட்டு திரும்ப கனெக்ட் பண்ண கனெக்ட் ஆகவே இல்லை.
minus u double dash is equal to f of x. 0 to 1. Take the domain to be 0 to 1. U of 0 is 0. U of 1 is 0. Then using the Galerkin finite element method. So what is the Galerkin finite element method? So this is the simple ordinary differential equation. I have taken this differential equation so that we can explain the concept easily. Okay. So consider. So what do we do? First step. So assume a smooth function, test function v of x, satisfying the boundary conditions v of 0 equal to 0, v of 1 equal to 0. Multiply this differential equation on both the sides by the function v. Okay, so you get minus u double dash v equal to f into v, and you take the condition 0 equal to 0, v of 1 equal to 0. Okay, with this condition, we try to multiply it by a test function v, and then integrate it by parts. Okay. Once we integrate it by parts, so what do we get? Integral 0 to 1 minus u double dash v into dx equal to minus integration by parts. I think you are familiar with integration by parts. Integral v is equal to uv minus integral v du. So here already there is a minus, so this is going to give you plus integral 0 to 1 dash v dash dx. Okay. So the boundary term will vanish because we are assuming that v satisfies v is 0, v of 0 is 0 and v of 1 is 0. So this boundary term is going to vanish, and you are going to get integral 0 to 1 u dash into v dash dx equals to integral 0 to 1 f into v dx. Okay. This is the first step. So first step, given any differential equation, we are trying to integrate it by parts and push the one derivative. You see here it is u double dash, but I have pushed this derivative onto v. Okay. So initially v is not having any derivative, but I pushed one derivative to v. So now you got u dash into v dash. This particular form, since this u from u double dash we have reduced it to u dash, this particular form is called as a weak form. That is why we are denoting it by the name weak form. Because of reducing one order of the derivative, the smoothness is reduced compared for the u. Okay. So this particular equation is called as a weak form. Okay. Then the second step is to generate a mesh. So given an interval, in our case the interval is 0, 1. So you take the interval 0, 1 and split it into partition, make partition, and put all mesh points inside the interval 0, 1. Okay. Consider this. So if 0, 1 is the interval, so the interval length is 1. So you divide 1 by n. Okay. N is the user specified. You want some 100 elements, so you simply put 1 by 100. Okay. So in general, if I say 1 by n, then that is your h. H is the step size. So it will be 0, first entry will be 0, next entry will be 0 plus h. Okay. Next entry will be 0 plus 2h, etc., etc. The last entry will be nh, and you know n into h is 1. Okay. So So this 0, 1 interval, we are trying to split this 0, 1 interval into partition, into pieces of subintervals. Here we are going to get n intervals. Totally we are going to get n plus 1 points, which can be denoted as xi equal to ih, I equals to 0, 1, 2, etc. n. Okay. So I is varying from 0, 1 to n, and xi is ih. Okay. So when I is 0, this is x naught. X naught is 0. When I equals to 1, your x1 will be 1, etc. When I equal to n, this xn is going to become nh. Okay. So we are partitioning the interval into several points. So this is the terminology used is called as mesh. We try to call this along with the mesh points, the entire domain, we are trying to call it as the mesh. Okay. Now, construct a set of basis functions. So next what do? We try to construct a set of basis functions. Okay. Consider phi of x. Phi of x is a basis function. Piecewise linear functions. So what is that? You take the interval xi minus 1 xi plus 1, 3 points. You just take 3 points, and then in xi minus 1 to xi, I define the function like this. In xi to xi plus 1, I define the function like this, and other places it is 0. Okay, so you are the entire interval 0, 1. You are in the entire interval 0, 1. So in other places, it is simply going to become 0. Okay, it is going to become 0 in other places. So you can look into this function. When x is equal to xi minus 1, this term is going to become 0. And when x equal to xi, this is xi minus 1, which is h. H by h is going to give you 1. Okay. Similarly, when I take x equal to xi here, this is going to give xi plus 1 minus xi divided by h, which is h by h again 1. If I replace x by xi plus 1, again xi plus 1 minus xi plus 1 is 0. Okay. So that means here it is 0 and here it is 1. This function, other function is 0, 1 at this point, 0 at this point. So this phi I function, we are going to get what is called as a hat function. Okay. This is in finite element literature, people call this as a hat function because its shape looks like that. Okay. Now, what is the next step? The next step is we need to construct. You know that here we have finally got the weak form, integral 0 to 1 u dash into v dash, integral 0 to 1 f into v. Okay. Now this u is an exact solution, but as I told you, for all practical purposes, we cannot compute this exact solution u. The exact solution u will be unknown. So what do? We do not have any, we do not know the exact solution. So what is the next step? So the next step is we try to approximate this u by another solution, finite element solution called UH. Okay. That is what we do in the next step. So assume, represent the approximate solution by a linear combination of the basis function. Okay. So UH, I introduce the finite element solution UH of x is equal to summation j equal to 1 to n minus 1, Cj phi j of x. Here we are excluding j equal to 0 and j equal to n. Okay, because our boundary conditions are already given to us. U at 0 and u at 1 is 0. Okay, so using the boundary condition, we can compute a C0 and a Cn. So those constants are not needed. That is why in this particular form, I have only considered j starting from 1 up till n minus 1, Cj phi j of x. Okay. Now you should be familiar, you should understand that this pj we are using the word basis functions. Okay. So in your linear algebra, you might have heard this term basis, vector space, basis, etc. This pj function happens to be a basis function. So so any function in the vector space can be written as a linear combination of Cj into Pj of x. Okay. Pj's of x are the basis functions and Cj's are the unknowns. Okay. So these are the unknowns which we need to compute. So this UH of x is the approximate solution, the finite element solution. So wherever there is a u, I'm going to replace that u by UH. Okay, that is the idea. Okay. So we had the weak form integral 0 to 1 u dash into v dash dx is equal to integral 0 to 1 f into v dx. Okay. So integral 0 to 1 uh dash v dash dx equal to integral 0 to 1. Yeah, doubt? Somebody is having a doubt? Yes? Yeah? Yeah, what is the doubt? Yeah, what is the doubt? Somebody just asked a doubt. It's not expanding. Yeah. Okay. I think I will proceed. Maybe the person has raised a doubt. Okay, you can note your doubt. I will proceed. Okay. So you have this u dash into v dash. So this u dash integral 0 to 1 u dash v dash dx is integral 0 to 1 f into v dx. So integral 0 to 1, I am replacing this u by the approximate solution UH. Okay. So this is UH dash v dash dx equals to integral 0 to 1 f into v dx. Now this u exact solution is replaced by the approximate solution UH. So that's why we are getting the derivative UH dash. Okay. So this u is replaced by UH dash. U is the exact solution, UH is the approximate solution. So we are replacing the exact solution by the approximate solution. Of course, by doing that, we are introducing some errors. Okay, some errors are introduced. We'll see about the errors later. So integral 0 to 1, we know the sum this UH is expressed in this fashion. So if I find UH dash, then UH dash is going to be summation Cj into Pj dash x. Okay. Cj's are constant. Only Pj is a function of x. So we are going to get Pj dashed of x. Okay. We are going to get Pj dashed of x. Okay. Fine. So you substitute the expression for UH inside this integral. So you are going to get Cj, Pj dash v dash dx, and the summation j equal to 1 to n minus 1 Cj, integral 0 to 1, Pj dash v dash dx, integral 0 to 1 f into v dx. Okay. So this term is, you can pull the integral outside, the summation outside, because this is a finite summation and this is the integral 0 to 1. I can pull the summation outside and make the integral 0 to 1 Pj dash v dash dx equals to integral 0 to 1 f into v dx. So finally we get, so what we do is, we have this function v. I'm going to replace this function v by the basis function. Replace v by one of the basis functions, pi. So in the first case you put p1, next equation you take p2, etc. for v. Okay. Take your v like that. So when you consider v in that fashion, v of x as phi 1, phi 2, etc. phi n minus 1 successively. So we finally get into what is called as a system of linear equations. Okay. We get into a system of linear equation. So in the first equation, your phi1 dash is fixed, phi1 dash, etc. phi1 dash, pn minus 1 dash dx, etc. Integral 0 to 1 f into phi1 dx, etc. So this is how you get the system of linear equations. Okay, you get into a system of linear equations. We need to solve the system with this linear equations, c1, c2, cn minus 1, cn minus 1, etc. Okay, this is how we have to solve this linear system to find the coefficients c1, c2, etc. cn minus 1. So this is the matrix. I am representing this integral in a different format. I am trying to put that integral as a of vi pj equals to integral 0 to 1. So this term I am denoting it by a of vi pj. So in the matrix notation we can write it like this. This a of vi pj is called a bilinear form, okay, since it is linear with each variable, and this is called a linear form. Okay. Since if vi are the hat functions, then in particular you can get 2 by h minus 1 by h. Okay. You get into what is called as a tridiagonal system for a particular basis function which we have introduced in the previous slide. This becomes like this. Okay. This is going to become something like this, the tridiagonal system. Okay. I'll explain to you how we are getting this tridiagonal system. I'll explain to you later. Okay. Once we obtain this linear system, we have to solve this linear system of equations. Okay. to obtain the coefficients C1, C2, C3, etc., Cn minus 1. And finally, we try to carry out the error analysis. Okay, anyhow, so first we will go how do we implement this in how do we write and implement this. I'll go to the implementation aspects. Okay, now consider this basis function. Okay, in the couple of slides before we have seen this basis functions. So the basis functions are defined like this. Okay, start from the x0, x1, x2, etc., xm. Remember, whenever we took that summation, I have taken the summation from 1 to m minus 1. Okay, the summation j varies from 1 to m minus 1. We are not including 0 and m. So we need not worry about the phi 0. Only we consider phi 1 and phi m minus 1. Okay, we need not worry about phi m because we are looking into j varies only from 1 to m minus 1. These are the basis functions, hat functions, which we have defined in the couple of slides before. We have defined this hat function. So see to that whenever I take the interval x0, x1 and x2, your phi1 is determined only in x0, x1 and x2. Okay. Next function is phi2. Phi2 is defined only in x1, x2 and x3. Okay. So it is defined like that, etc. till xm. So we will be considering only this function phi m minus 1. Phi m minus 1 is defined in the interval xm minus 2, xm minus 1, xm. That is how it is being defined now. So in the terminology, already I have introduced the terminology. x0 is 0, and you say x1, x2, etc. the other points. xm will be equal to 1. Hi will be the difference between xi plus 1 and xi. That is your hi. That is the mesh size for each interval. So I, as I mentioned, this I is varying from this. Now xi is called a node or nodal point, and this interval we are trying to call it as an element. Okay. xi comma xi plus 1, this is called as an element. Okay. Then this h is nothing but maximum of I varies from 0 to m minus 1 is the mesh size. Okay. This determines how the partition is. Okay. Usually this hi is going to be uniform. But in this case we are considering non-uniform hi. For each interval hi is different, and you are considering the maximum of that. Okay. So h is equal to maximum of I lies between 0 to m minus 1 hi. Okay. Then we are trying to define a finite dimensional space. Okay. VH is a finite dimensional space. VH is a finite dimensional space. So we are constructing a basis for this finite dimensional space, phi 1, phi 2, etc., phi m minus 1, which is contained in VH, that are linearly independent. Okay. So in linear algebra, you know that we try to call something as a basis if it is linearly independent and it has to span the whole space, and it has to be linearly independent. Then you try to call that as a basis. Okay. So here this P1, P2, etc., Pm minus 1 are linearly independent by the construction, and it satisfies this condition. So VH is a space spanned by the basis functions. Okay. So VH will be nothing but VH of x, such that each element in VH can be written as a linear combination of alpha j phi j. Okay. The simplest finite dimensional space is the piecewise continuous linear function space defined over the mesh. Okay. Piecewise continuous function. So that we have defined already. Okay. So you take the capital VH, this is a VH of x. VHx is continuous piecewise linear, and it satisfies this condition. VH of 0 equals to VH of 1 equal to 1. Okay. VH of 0 equal to VH of 1 equal to 0. And then we'll try to show that this finite dimensional space VH is having a dimension. Okay. What is the dimension of the space VH? Okay. So we are trying to construct a linear function L of x, which is equal to L of xi x. So this is a linear function. You can see that when x is equal to xi, this term becomes 0, and this term gives you 1. So it gives L of xi. When x is equal to xi plus 1, you see that this term is 0, and this term is going to give you 1. So it gives you L of xi plus 1. Okay. So there are nodal values. What are the nodal values? you get L of x1, L of x2, etc., L of xm minus 1. So you get m minus 1 values you get. Okay. For a piecewise continuous linear function over the mesh. So in addition, you have two more, L of x0 and L of xm is 0. So given a vector L of x1, L of x2, etc., L of xm minus 1, because these are the points, okay, we can construct a VH in the finite dimensional space by defining VH at xi is equal to L of xi. Okay. On the other hand, given VH, we can get a vector, this one belongs to Rm minus 1 by defining Vx1, Vx2, Vx at xm minus 1 by L of x1, L of x2, etc., L of xm minus 1. Okay. So there will be a one-to-one correspondence between the VH and the m dimensional space. Okay. There will be a one-to-one correspondence between VH and the Rm minus 1. So this VH has the finite dimension m minus 1. So the dimension of the finite dimensional space is m minus 1. Okay. Next, we need to find the basis functions. Okay. How do we find the basis functions? So the criteria is the basis function has to be simple and it has to have compact support. Compact support means it is 0 everywhere except the small region. Except a small region, it is 0 everywhere except a small region. Then it should meet the regularity requirements. That is, it should be continuous and differentiable except at nodal points. Okay. The simplest idea is the set of hat functions. Simply we try to take what is called as a hat function. So phi1 of x1 is equal to phi1 of x1 is 1, etc. That's what we have seen. Okay, the hat function is what we have seen. Phi1 starting from phi1, etc. Phi m minus 1. Okay. So you have m minus 1 functions. Okay. They satisfy this property, Kronecker delta property. That is phi I at xj will be delta ij. When I equals to j, it is 1, it is 0 otherwise. So this is the basis function which we are considering, and the reason for considering this basis function is our program looks very simple. The final matrix reduces to what is called as a tridiagonal matrix. We have already seen the tridiagonal matrix, right? So finally our matrix, it becomes a tridiagonal matrix. That is the essential idea is to make the matrix look simpler so that it will be easier to perform the computation. Okay, write a program and perform the computation. That's the idea of developing a simpler set of basis functions. Okay? And this basis function gives us a simple matrix. Okay. Now let me come to this portion. So you see that we are already splitting this interval. Given an interval, we are trying to split this into smaller pieces. Omega 1 is a smaller interval. Omega 1, omega 2, omega 3, etc. On omega 1, you are going to get this function. Okay. And omega 2 this function, etc. Okay. Now what we are going to do is, locally if you see in one interval, basically you have only two types of functions in one element. Consider, see this slanting line, this function and this function. Only two types of functions are involved in every interval. Okay. I am giving them a separate name. I am calling that as psi1, psi2, and on the superscript I am putting 1 to say that this is from omega 1. These functions are coming from omega 1. Okay. Similarly, omega 2, I am doing the same thing. Xi1, Xi2, and superscript I am making it 2. Okay, superscript I am making it 2, so that to say that this belongs to omega 2, this Xi1 and Xi2 belongs to omega 2. Similarly, Xi1 and Xi2 for omega 3, etc. So for each element or for each interval, I am going to consider two functions, psi1 and psi2. So this phi1, phi2, etc. I am going to call as a global basis function, and xi1, xi2, etc. I am going to call as a local basis function. Okay. One is a global basis function, another one is a local basis function. This is the basis function which we have already defined, the hat functions. Okay, a couple of slides ago we have seen this, the hat functions. Okay. Now. Okay, so now this is what the finite element solution we have assumed, UH of x, summation j equal to 1 to m minus 1, alpha j phi j of x. Okay, okay, this is the finite element solution which we are assuming. Now, so if you see the matrix, what was the final matrix we had? The final matrix we had is integral phi I dash into phi j dash. integral of phi I dash into phi j dash is the integral. Now what I am going to do is, that is the stiffness matrix. That is, we call that matrix as the stiffness matrix. Okay? We call that matrix as the stiffness matrix. So, so what do we do? So you take this, you take the matrix integral 0 to 1. First entry is phi 1 dash into phi 1 dash, that is phi 1 dash square. Second entry is 0 to 1, phi 1 dash into phi 2 dash dx, etc. So likewise you have a matrix. Now what I am going to do is, I am going to split this integral into several subintervals. Okay, split this integral. You can write it as integral x0 to x1, x1 to x2, x2 to x3, etc. like that, right? You can put it like that. So that is what we are trying to do here. Integral x0 to x1, phi 1 dash square dx. I am making all this integral as first in the interval x0 to x1. Okay. Then I am making a plus summation. Integral x1 to x2. I am making all the terms in the integral, all the terms in the matrix in the interval x1 to x2. Okay. I am splitting the 0, 1 interval into x0 to x1, x1 to x2, etc. Okay, till xm minus 1. That is the idea. Xm minus 1 to xm. Because you have the full integral. Okay, 0 to 1. So you are going to get the sub matrices into sum of several matrices. Each matrix are like this, and each are written on each interval. Remember, in finite element terminology, we are calling this interval x0, x1 as an element. Okay. So this matrix corresponds to the first element omega 1. This corresponds to the second element omega 2, because it is in the interval x1 to x2, etc. This matrix is written in the element. Okay, so that is the last element, okay, omega m. So that is how these are being written. We are trying to do it, split this interval into several elements, find the matrix on each element. Okay, so this is on only one particular element. Okay. Now we can see one thing we can understand here. Let me go back to that again. Yeah, because from there I wanted to explain you something. Not this expression. Yeah, this from here I wanted to explain you something. Now if I consider x0 to x1, integral x0 to x1, if I consider, you have phi 1 dash square, okay, phi 1 dash square. Now what is your phi 1 here? So this is the small portion, you see. Forget about phi 0, we don't need phi 0, we want only phi 1. So phi 1 is defined in the interval x0 to x1, it is defined like this line, right, that small portion. So that means phi 1 is defined in the interval x0 to x1. Okay. So your first term is integral phi 1 dash square. Okay. What is the next term? Next term is integral x0 to x1, phi 1 dash into phi 2 dash. Okay. Phi 1 dash into phi 2 dash. Now consider the integral intervals x0 to x1. See what is your phi 2 function. So phi 2 function starts only from x1. Okay, this is this hat function. This is the hat function corresponding to phi 2. But if you see your interval x0, x1, there is no phi 2. So that means phi 2 is 0 in the interval x0 to x1. Phi 2 is 0 in the interval x0 to x1. So what will happen to the integral? Integral x0 to x1, phi 1 dash into phi 2 dash. So what will happen to that? That is going to become 0. What about the next terms? All other terms in the row, except in the first row, except the first term, all other terms are going to become 0. Because in each interval, only some functions are defined. It takes non-zero values. Other places it becomes 0. Right? A function is defined like this. This hat function is defined only within this interval. Outside that interval, that function is 0. Okay, that is how we are defining the basis functions. Okay, so that helps us here. Okay, that is the idea. With that, what we can do is, okay, so with that, so once we split this into smaller intervals, you see that here phi 1 dash square dx x0 to x1. Only this term is non-zero. This term is 0. All other terms are 0 in the first row. Are you able to understand? Excluding this term, all other terms are going to be 0. This term also 0. This is the second row, third row, fully everything is 0. Only first row, the first entry is non-zero. All other terms are 0. Plus. Similarly here again. Now you are thinking, considering x1 to x2. Again x1 to x2, if you consider this, these two terms, this and this, will be there, remaining terms will become 0. Second row, first and second term will be there, remaining terms will become 0. If you keep on sum it up like that, so that is what I'm going to show you here. Okay. So this is how you get integral x0 to x1, phi 1 dash square dx. First entry is non-zero, all of the terms are 0. Plus the second term, x1 to x2, you get only the first 2 by 2 portion. All the remaining terms are 0. Plus the third term, the final term. The final term again you are going to get only one term, phi m minus 1 dash square dx, because there phi m minus 2 will not come into picture when you consider xm minus 1 and xm. Okay. So all of the terms are going to become 0 here, here and everywhere here. So finally we need to add these up. Okay, that is the idea. But we can notice here, one thing we can notice here in all these matrices, there is a portion of 2 by 2 matrix. Okay, you consider this one, integral x1 to x2, this 2 by 2 matrix here. Here also you see 2 by 2 matrix. Of course, only this portion you have one entry. All other places you are going to get, excluding the first and the last, everywhere you are going to get a 2 by 2 portion. Understand? So this 2 by 2 portion is on a particular element in each element. Okay, and this phi 1, phi 1, phi 2, I can replace it as psi 1 and psi 2. Okay? So to make it local. So that is the idea here. So what we are doing, you can say an element KIE integral xi to xi plus 1 phi I dash square phi I dash phi I plus 1 dash phi I plus 1 dash phi I dash. Okay, we can make it into a 2 by 2 form. Okay, locally for each I I can make a locally 2 by 2 matrix. It is called as a local stiffness matrix. Similarly, the right hand side also you can make it as a like that. Okay, you can make it a summation of several vectors. Okay, the first vector here, second vector is this, third vector is this, etc. The last vector is this. That is essentially what we are doing, is we are trying to split the integral 0 to 1 into intervals of different elements. We are splitting into different elements. Element wise we are finding it and then adding. Okay, that is the idea. Element wise we are trying to find it and then finally add all these things to get the integral on 0 to 1. That's the idea. So to this end we are defining these basis functions psi I ex, psi I plus 1 ex. Okay, and then you differentiate this psi I, so you get psi I dash, which is minus 1 over hi. This is 1 over hi. Okay, just differentiate with respect to x. Okay. So in this case you are going to get a constant because this is a linear function. Your psi I and psi I plus 1 are linear functions. So if I try to differentiate that, I am going to get only these constants. The derivatives are simply constants. Now let us come to this local integral portion. What is the integral portion? Integral xi to xi plus 1 psi I dash square dx. Okay, that is simply 1 more hi square dx, 1 by hi. Similarly, psi I dash into psi I plus 1 dash. Okay, because this is minus 1 by hi and 1 by hi. So you will get it like this, etc. Okay, simplify this. So I am going to get a local stiffness matrix like this, 1 by hi minus 1 by hi minus 1 by hi and 1 by hi. This is a 2 by 2 portion. Now this 2 by 2 portion has to be added everywhere. Okay, you see here, everywhere you get a 2 by 2 portion. You compute the 2 by 2 portion and add it in the corresponding location. You see in this, in the second matrix, the 2 by 2 portion comes in which location? 1, 1, 1, 2, 2, 1, 2, 2. Okay. In this matrix, it comes in the location 2, 2, 2, 3, 3, 2, 3, 3. You understand? So that is how it comes. Okay, so we need to understand how we have to, where we have to place this 2 by 2, which location, and correspondingly you have to add the matrix. That's all. So once we are done with this local matrix, finally how we assemble. So consider the matrix A, which is having m minus 1 by m minus 1 matrix. All the entries are 0. Now I take the first entry, 1 by h0. I place it in the position, first position. Then what I do? Then I know I have this 2 by 2 portion. Where do I add this? This 1 by hi you have to add with this guy, 1 by h0. So that will be, this is I equal to 1. Okay. So this is 1 by h1 will be added here. The second entry will be minus 1 by h1. This is minus 1 by h1 plus 1 by h1. The next entry again, which location we have to add? Already this is 1 by h0 plus h1 minus 1 by h1. This is okay. Now this location you have to add. So 1 by h1 plus Now you take I equal to 2. So this will be plus 1 by h2, minus 1 by h2, minus 1 by h2, 1 by h2. So we have to keep on add that 2 by 2 portion, 2 by 2 submatrix portion in the corresponding positions. So this is traditionally people call this particular technique as assembling. Okay? This is called as the assembling. Once we assemble that, finally you see that we are going to get into a matrix of this format: 1 by h naught plus 1 by h1 minus 1 by h1 minus 1 by h, etc. You are going to get what is called as a tri-diagonal matrix. That is, this is a main diagonal, this is a sub-diagonal, and you have what is called as a super diagonal. And all the remaining entries are going to be simply zeros. Okay? All the other entries are simply going to be zeros. Okay? Similarly, you can do it for the right hand side. Same thing we have done for the right hand side. I think I have already shown you here. Right hand side, you have to do the same thing over each entry, then finally add it up. Okay, that's the idea. Okay, so finally you do that. We get into a system of you get into a linear system, and we try to solve the linear system. Okay. So now what I will do is I will explain this in a program. Okay. So I think some of you will be familiar with MATLAB. So what I will do is, okay. So what I will try to do is, okay, let me, okay, first. So I will try to show you whatever we have done now. I will try to show you that in MATLAB. Okay. Just give me a second. I'm trying to open this MATLAB. Okay. Okay. So now, yeah. So now what we will do is share. Okay. So whether everybody is able to see the MATLAB? Yes. Are you able to see the MATLAB version?
Yes, sir. Yes.
Yeah. Okay. So now let me show you the program. Okay. So open. Okay. Yeah. So are you able to see this program? FEM1D.m. Yes.
Yes, sir. Yes, yes, sir.
Okay. So I will just explain this. Whatever we have seen, I will try to explain that in our program. So you consider, see this n equal to input of enter the number of elements. First I am trying to enter the number of elements. Okay. So I am asking what is your capital N. Okay. So capital N, if you give, then you can find H from that number of elements. Okay. This talks you about the number of elements. Okay. Then what do I do? Then you take this m equal to n plus 1. So you have n elements, capital N elements. So total number of points will be n plus 1. Okay. Capital N plus 1. Okay. So that I am defining. Then I need to split it into intervals. You need all the mesh points. So what you do? I say x is equal to LIN, linspace of 0, 1, m. Okay. So linspace is a simple command. If you want, I can show you. Linspace, you can see linspace is a simple command. If I take 0, 1, 4, if I say, it gives you 4 points. Okay, it gives you 4 points in between 0 to 1. Accordingly, it assigns 1 by 3. It takes the space as 1 by 3. So 0, 1 by 3, 2 by 3, 3 by 3 is 1. You get 4 points. You have to tell 0, 1, and then how many number of points you want. Okay, so that is the command linspace is used. So typically I am using a linspace 0, 1, m, because we are having m points totally. This is a totally, maybe we can say the total number of mesh points. Total number of mesh points. Okay. So capital M. So your x, no, this total number of mesh points. You are saying total number. and these are your mesh points. Okay, we are trying to put the mesh points. Okay, then so X creates all the mesh points. Then what do we do? Then what do I do? I simply take H, which is the step size. Okay. See this linspace command, it automatically takes that H. But then we need, specifically we need that H value. So what I do is, you know that we are taking a uniform partition, the linear space, a uniform partition. So you find the length between any 2 points. Something like x of 2 minus x of 1, it gives you H, which is the mesh point. X of 2 minus x of 1, which is the mesh point. And then x of 2 minus x of 1 is the interval. So that is I am spacing that as H. Okay. Now if you want, we can put it here. We can say this is the, it is called as mesh size. Mesh size. Okay. Or step size we used to say. Okay. Then I am defining a matrix, global matrix A equal to sparse of m comma m. Okay, sparse of m comma m. It's a global matrix of size m by m. Remember here I am using the word sparse because sparse of m comma m means it will not create full m by m matrix. Remember our final matrix is tridiagonal. That means many entries are 0 except the 3 diagonal entries, all the entries are 0. So there is no need to create a matrix which can hold all the entries. Because there is no need to waste the memory. There is no need to waste the memory. I am saying a sparse matrix. That means it understands that not all the entries are, only few entries are going to be non-zero. And that is the understanding when I say sparse of m comma n. The next, the right hand side vector, global load vector. Again I am saying f equals to zeros of m comma 1. Okay. Then we are talking about this local matrix. We need to talk about the local matrix. You see, the local matrix is capital AA. Okay, capital AA, I am calling the local 2 by 2 matrix. 1 by H, minus 1 by H, minus 1 by H, 1 by H. Local stiffness matrix. Okay. This already we have seen in our explanation, right? And then I need a local load vector. That is a 2 by 2 vector. Okay, 2 by 1 vector. Zeros of 2 by 1 vector. This also we have to assemble. So that finally you get into a matrix of size capital A and capital A. Finally we need to get capital A and capital A. Fine. Now, okay. Finally, I am trying to assembling of the matrices and vectors. Okay. So this portion is called as the assembling. So this is an element. We are starting to, maybe if you want here, we can mention varying element over I. Okay. We are varying the element over I. So that means starts from element 1 to element m minus 1. Okay, that is the one. So f equal to load underscore val. So I want to create the local load vector, compute the local load vector, and then capital A. This is the place we are trying to assemble. You see here, capital A. I will come to this f load underscore val. I will show you. I will come to this portion. Capital A of. I will try to show this capital A. Capital A of I is to I plus 1, comma I is to I plus 1. Okay. Capital A of I is to I plus 1, comma I is to I plus 1 is equal to capital A of I is to I plus 1 with this one. Okay. Plus AA. This AA is a 2 by 2 matrix. Remember, this AA is a 2 by 2 matrix. Okay. This AA is a 2 by 2 matrix. So this you see when I is equal to 1, this will be 1 is to 2, comma 1 is to 2 is equal to 1 is to 2, comma 1 is to 2. Then when I is equal to 2, this is 2 is to 3, comma 2 is to 3, 2 is to 3, comma 2 is to 3. Okay, so this is how we are getting into that sub portions. Okay, this is how we are trying to get into the sub portions. So. So locally we are having this 2 by 2 matrix, adding it in the corresponding location in the capital A matrix. You know the capital A matrix is a global matrix. Capital A matrix is a global matrix. So simply I am adding this local matrix onto the corresponding locations in the capital A matrix. And finally the right hand side also. Anyhow, now I will try to show you. The local load vector which I mentioned you. I'll try to show you. So function is equal to f underscore load value x1 comma x2. Okay, so we are using the quadrature idea to calculate f of 1, f of 2. Here I am choosing the function to be pi square sine pi x, pi square sine pi x, and I am evaluating that function using the Gaussian quadrature. If you are familiar with the quadrature idea, any integral can be written as the point, the function evaluated at the point into the corresponding weight. Okay, how many points you have and how many weights you have. Okay, so there is one more quadrature. You have one more function which says if I take quadrature 2-point quadrature, then I have 2 points and 2 weights. 3-point quadrature, then I have 3 points and 3 weights, etc. You can see the point values are nice between -1 and 1. Okay. The points are defined only for the integral limits from -1 to 1. So we have to accordingly change. So what do we do here is, I am shifting the quadrature point to the interval x1, x2. You take the points x1, x2, -1 to 1 is the quadrature point is initially, this point is initially defined in the interval -1, 1. I am shifting that to the quadrature point x1, x2 by doing this transformation. So this C is going to be a point in the interval x1, x2, inside the interval x1, x2. And then I evaluate the function pi square sine pi x. And then I'm going to do the quadrature, that is this value, ft, that is pi square sine pi x value into the basis function, because the integral is integral f into phi 1, integral f into phi 2. So integral f into phi 1, integral f into phi 2 at that point. Okay. So likewise, I am doing it for all the points and summing it up, sum 1, sum 2. Initially, sum 1 and sum 2 is 0, then you keep on add that. Okay. So 1 by h is the factor which comes in the substitution of integration. We are getting this 1 by n as a factor, 1 by h as a factor, the substitution integration, it comes because of the integration portion. Then simply we get f of 1 equal to sum 1, f of 2 equal to sum 2. Okay. So this is the load vector. It gives you an f vector, which is a 2 by 1 vector. Okay. So this is what you had in this local load vector. Then that also I am assembling. F of I is to I plus 1 equal to f of I is to I plus 1 plus f. This small f, okay, is the local load vector being assembled, and we are adding it onto this capital F. Okay. A of 1 comma colon equal to 0. So now we need to talk about the boundary conditions. So remember the boundary conditions, u at 0 and u at 1 is 0. So what do we do is, I take the first row. Initially I am putting all the entries are 0 of the first row. 1 comma colon means it is the first row. M comma colon means it's the mth row. So both all the rows entries I am making 0 initially. Then what I am doing is I am making this a of 1 comma 1 as 1 and a of m comma m as 1. Okay. So in the first row, first location is 1. The last row, last entry is 1. Okay. Then f of 1 is 0 and f of m is 0 because the boundary condition is 0. Okay. So the first row and the last row corresponds to u1 equal to 0. The last row corresponds to um equal to 0. I am accordingly modifying the entries of the matrix. Okay. So after applying the boundary conditions, finally I get into the linear system, ax equals to f. So I need to solve this ax equals to f. So in numerical analysis, we have a solver called as Gaussian elimination with partial pivoting. This is already available in MATLAB with the help of the slash operator. So simply we give a slash f. We simply give a slash f. So this is the Gaussian elimination with partial pivoting. Okay. This solves the linear system, and then it gives the answer here, u approximate. Okay. Then the u exact, what is the exact solution? We already know the exact solution for this problem is sin pi x. Okay. So now I am trying to plot exact solution, which is a black with the minus symbol. The line will be black line with the -1 dot dot 1, and the approximate solution with the yellow, approximate solution with yellow and a star. Okay, I'm making the axis, x-axis 0, 1, x-axis 0, 1, and the y-axis range also 0, 1. Okay, so now let me show you this. We will try to plot this, and I will show you the result, whatever we have done. Okay, so this is. So initially it is asking for the number of number of the elements. Let me give 100 elements. Okay, 100 elements. Okay, take some time. Yeah, so you got this is the plot of the solution. Okay, this is the plot of the solution. You see here. Uh, you see here. This is the plot of the solution. So the black one with the dot dot, the line is the exact solution. And the yellow one is the numerical solution. And here you see that there is no difference between this one, exact and numerical. Okay. This is only for the graphical purpose. And to validate it more correctly, what we do is we try to take this L2 error and H1 error, this one, 0.40. These are the error in the L2, H1 now, LN. I'm not going into that portion. That has some more tools. We need some more mathematical tools to determine that one. Okay. Yeah. Okay. So yeah. So I will start with this. Yeah. Yeah. So any questions? Yeah. Any questions? You can ask me. Raise your hand. Raise your hand if you have any questions. Raise your hand. Or you can either raise your hand. Yeah. Raise your hand, or you can type your question in the. You can type your question in this. Okay. In the chat, you can type your questions in the chat also.
Participants, please, do you have any doubt, please ask.
Sir, I have one doubt, sir. I'm Shweta Sinha.
Okay, yeah, tell me, yeah.
Sir, when you were doing the construction of variational formulation, at that time you integrated from 0 to 1.
Yes.
So while doing the integration by parts, it was one single term was coming at boundary, like u dash
Yeah,
v.
exactly. Yes, yes. Yeah.
You were saying it will become 0. I wanted to know how it will be 0, because the boundary condition at u it is given 0, 0, 1, 1. And they have not told, it is not given that del u upon del x.
No, yeah, I will see that the value. See, we are assuming that it is not because of u that term is vanishing. The boundary term is vanishing because of v, because of the function v. Are you able to get me? The function v. You have the u dash into v evaluated on the boundary 0 to 1. Okay.
Okay, yes, sir.
We are taking the test function v such that v of 0 and v of 1 are 0.
Okay.
So u dash we don't have any idea about u dash. So that term will be u dash of 0 into v of 0, u dash of 1 into v of 1 minus u dash of 0 into v of 0. Because v of 1 and v of 0 is 0, the term vanishes.
Okay, it is true always that text function at boundary will be 0?
Yeah. We see test function, we are taking our test functions like that. In fact, you have seen that in the later stage, we are replacing the test function by the basis functions. Yes?
Yes, sir.
I have replaced the test function v by a basis function.
Basis function, right.
So during the variation formulation, there is no issue. We can choose a test function. In fact, the Galerkin formulation, we have to choose the test function v satisfying the same condition as your u. Okay, that is the idea of Galerkin.
Okay, sir, I have one more confusion. Like when we are starting, we are integrating in whole domain when we are applying finite element.
Yeah.
Then we are shifting to the element wise.
Yes.
So when we have to perform this in a programming, how this is shifting is occurring? Like I am confused to which one to apply. Directly integrate to the boundary, or to apply element-wise integration by parts?
No, see, the problem, you have to understand one problem. Even though mathematically I have told you that, see, there are two sets of functions I have introduced. You remember that I have shown phi 1, phi 2, etc. Phi m minus 1. Okay, this is one set. This is called as the global basis function. Okay.
Yes, sir.
This is with this phi, the function phi 1 to phi m minus 1 itself. is enough to explain the finite element method. Okay, but when I go for programming, it is not easy. It is not easy to find out this phi1 to phi m minus 1 basis
Yes.
functions, because when the m is increasing, when I do program, when I perform programming, the number of elements, see in the example I have told you the number of elements is 100 I have taken. Okay,
Yes, sir.
that means for 100 elements you are going to have phi 1, phi 2, etc., phi 99. Those many basis functions are there. Okay,
Right, right.
so for computation it is going to be hectic. So what we are going to do is, we are in the each interval we are taking a local basis function. That is what I have defined
Oh,
you as
oh, yes,
psi 1
yes,
and psi 2. You remember psi
yes,
1 and psi 2?
yes, sir. Yes, sir.
Psi
Zyvan
1
and
power
Zy.
1 and psi 2 power 1 for the first
Right,
element.
right,
So
right.
locally we are doing it, and otherwise it becomes complicated when I am going to do it for all the basis functions for the entire element, entire domain. If I am going to define the basis function, that is computationally it is not feasible.
Okay. So for computational purpose, we divide into element. Otherwise, it is globally integrated. Right.
Yeah, you can do integral 0 to 1, but for practical purposes we cannot do that.
Yes,
I
sir.
can define phi1, phi2, etc. But when the
Mm.
size of number of elements are increasing, you need to
No.
keep in track of the basis functions in that fashion. The split basis
Yes.
function will be there, right? You need to keep in
Yes.
track of that accordingly,
Right.
and then the integral and all you have to perform. So this becomes
Okay.
very simple. Actually, you don't see much here, but when you go to two dimension, okay, this is one
Yeah.
dimension. If you go to two dimension, you will see that how important this element wise calculation is needed. How much it is needed. The
Okay.
element wise calculation is needed when I go to a higher dimension. Two
Mm.
dimension and above, if you go, you will see the importance. Yeah.
Yeah. Okay, sir. Thank you, sir. And sir, the code was not visible. What you were typing in your editor window, it was not
Oh, I
visible to
see.
me. So,
Oh,
I,
the editor is visible. The code is not visible, is it?
yeah, the command window was
I
visible. The
have
editor window was
shared. Yeah,
not
I
visible.
have shared. Okay, I have shared this. I think it should both should be shared. Okay, I will look into that. Yeah.
Okay, sir. Thank you, sir. This was my query. Thank you, sir.
Sir,
Yeah. Tell me, sir. Yeah.
good afternoon, sir.
Yeah. Yes, sir. Ask your question.
Sir, your presentation is very nice, sir.
Okay. Okay.
Okay, thank you very much, sir. Sir,
Okay.
that's only I am asking. Thank you, sir.
Okay.
Any
Yeah.
doubts from
Hello, madam.
inside, sir?
Madam is there?
Sir,
Yes, madam. Any other questions? Or we can.
any other question from participant side, please ask. Okay, sir, no more questions, sir.
Okay. Okay. Fine.
Sir, can I conclude, sir?
Yes, madam. Yes, madam.
Thank you so much, sir. The session was very interesting and informative. Um, yes, we heartfully accept you have fulfilled our expectation about mathematical analysis of finite elements method through MATLAB. I hope all the participants learned something new in this session. Thank you so much, sir, for accepting my invitation in your busy schedule. Thank you so much, sir.
Okay.
Also, I have to thank our college secretary, principal, IQSC coordinator for constant support to conduct the webinar. Hearty thanks to all the participants for your patience and support. Thank you. Thank you so much. The feedback link will be posted in your chat box. It's open only 30 minutes. Thank you.